This begins screencast number 2 of chapter 2, and we're looking at the periodic table of elements. All of the known elements are listed in order going left to right according to the number of protons in that particular element. So for example, we have 1 proton and it's hydrogen, and across here we have 2 protons, helium. And then we have 3, lithium, 4, 5, 6, 7, 8, 9, 10, and then the next row. So they're always going from left to right in an ascending order based on the number of protons. And again, remember, that's the key thing that determines what the element is. They're also grouped vertically, which is why there are some big spaces here, based on some chemical properties that we don't really need to explore here for environmental science purposes. So I want to explain next how these elements are named and symbolized with capital letters or a capital letter and a lowercase letter. So all elements have a symbol, and it's either a single capital letter or a capital letter followed by a lowercase letter. And some of them are very clear to us, like carbon is C, nitrogen is N, oxygen is O. Some of the names may be a little unusual to us. For example, down here at PB is actually lead. Now the word lead does not sound anything like P and B. That's because lead, the chemical symbol for lead, was derived from the Latin for lead, which is plumbum. P-L-U-M-B-U-M. So write that down for a second, P-L-U-M-B-U-M, and think if that has any, if there's any word in English that begins similarly to plumbum. So an English word that derived from Latin was plumbing, P-L-U-M-B, like plum. And actually it was derived because the ancient Romans, toward the end of their civilization, they lined their aqueducts with lead. And this led to neurological poisoning, which may have contributed to the fall of the Roman Empire. A little side note. Okay, so looking again at the periodic table, you can see you have some elements which we're familiar with that have relatively low number of protons, low atomic numbers. So carbon 6, oxygen 8, maybe moving down here a little bit to aluminum at 13, sulfur at 16, getting into higher numbers down here with lead at 82. So we're getting into larger atoms, larger elements. And then we look all the way down here. Let's look at uranium. Uranium has 92 protons in its nucleus, and it has even more than twice that number. You can tell by looking at the number down here. It has many, many more than 92 neutrons. So that makes it a very unstable element. It's so large, and it has a lopsided number of neutrons, and together that leads to having its radioactive chemistry. I'd like to take a moment here just to point out some of the elements that we will frequently encounter during the semester. So you should probably try to learn their symbols so they make sense to you. First, we have hydrogen over there with the H, followed by helium with HE. We also have carbon for the C, nitrogen for the N, O for oxygen. Fluorine is F. Think about fluoridated water, for example. And down here we have phosphorus, which is a big water pollutant, symbolized with a capital P. Sulfur, also a pollutant, usually from burning coal, and that's with a capital S. Let's see, I would like to move down to arsenic right here, capital A, lowercase s. That is a result of, again, burning coal and its runoff, and can also be quite toxic to wildlife, especially birds. And let's see what else I'd like you to know about right now. Lead, Pb, which I've mentioned already, and mercury is capital H, lowercase g. That's mercury. Whoops. And mercury is also a very toxic element. It's very toxic to the brain and the nervous system, especially in developing children. And let's see, we'll talk about that throughout the semester. And then we have uranium, which we'll talk about. It's capital U, and thorium is TH. And I think that should about do it for now. So next I have a set of definitions. I've been throwing around terms like element, so we need to take a few minutes to define the various terms, explain what they are, and give some examples. So the first is the term element. An element is a unique substance composed of atoms that can't be broken down by any physical or chemical means into smaller, simpler, and different components. So you can't break it down by physical means. So for example, you have a sheet of aluminum foil. You might physically rip it apart into smaller and smaller pieces. But even if you went to the teeniest size, way beyond what we could actually do, you would still have just one atom that had 13 protons, and therefore it is aluminum. An element also can't be broken down by any chemical means, not just physical means, into smaller, simpler, and different components. So if we go back and we look at carbon, for example, you can't, by combining, say, carbon with oxygen and getting carbon dioxide, you don't change the fundamental unit of carbon. It still stays there with its 6 protons, and oxygen still stays there with its 8 protons. So that individual unit can recombine with different elements, but the basic unit won't change. So that's what's meant by not changing in any chemical reaction. Now the next two vocabulary terms are close confusers, molecules and compounds. Molecules contain more than one atom. Okay, so oxygen that we breathe has 2 oxygen atoms combined, so it's more than one atom. Water has 3 atoms, 2 hydrogen atoms and an oxygen atom, and therefore it is also has more than one atom, and it's therefore a molecule. So the only difference here is if we move up to compounds, a compound is a molecule that contains 2 or more different elements held together. So all compounds are molecules, but not all molecules are compounds. So for example, water has hydrogen and oxygen atoms, so therefore it's a compound. But O2, the oxygen that we breathe, has 2 of the same elements. So the same type of atom held together, so it's not a compound. Very minor difference here. Last term on this page is ions. An ion is when you have either a single atom or a group of atoms that have an electric charge. They either have a positive charge or a negative charge, because if they have a negative charge, they have an extra electron either on that atom or a group of atoms. And if they have a positive charge, then that atom or group of atoms has lost an electron and it's been donated to something else. All right, so now we're going to look at how these are written and say what they are. So here we have water, which most people are familiar with, and it has 2 hydrogen atoms, 1 oxygen atom. So when you have one of a particular atom, the number 1 isn't really written here, it's just assumed. But when you have more than one of a particular atom, you designate it with a subtext 2, subscript 2. So one molecule of water, well, would just be, erase that 2 for now, H2O. 2 molecules of water, to designate that, we put a 2 in front of the molecule. So 2H2O means you have 2 water molecules. Now, if we wanted to know how many hydrogen atoms we had in 2 molecules of water, you would take the 2 here and multiply it by the number of atoms in that particular molecule. So in 2 molecules of water, we have 4 hydrogen atoms. And if you take the 2 and multiply it by our little imaginary 1, it also has 2 oxygen atoms. This here is carbon dioxide, which we'll talk a lot about because it is a greenhouse gas. And carbon dioxide contains 1 carbon, so the number is not written here, and 2 oxygen atoms, so we put a subscript 2, and these are held together. And if we had 6 molecules of carbon dioxide, we'd put the 6 out front here. And if we looked at the individual number of atoms, we would say that 6 CO2 molecules contain 6 carbon atoms, 6 times the 1. And it also contains how many oxygen atoms? Well, it would be 6 times the 2, or 12 oxygen atoms. And here I have an example which is sodium, and a sodium is a single atom, single element here that has a positive charge. And that positive charge or negative charge is written as a superscript, plus or minus. And then down here we have a molecule, phosphate, which contains 1 phosphorus atom, 4 oxygen atoms, and here we just have 1 molecule. And phosphate exists with a negative charge on the entire molecule. That 3 minus here is not just on the oxygen the way the plus here was on the sodium. So 3 minus refers to this entire molecule having a negative charge of 3. Okay, I'm going to pause Chapter 2 Screencast 2 here and move on to a new recording.